So welcome everybody. Good morning or good afternoon, good evening, wherever you might be. I know that many people are connecting from many different places. So we are very glad to have you all here. Thank you for joining us. This is now the 10th plenary talk we have for the Student Symposium in Combinatorics. And it's already the last day, so it's exciting and a bit sad for us. But for those of you who are joining us for the first time, welcome first. So this is a conference run by students and for students, mainly in combinatorics, but also in related disciplines. And we are very grateful. First, I've mentioned the support of our sponsors, Matrix, OSTMS, AMSI, and the School of Math and Stat from UNSW, who helped us put this symposium on track. And for today, for this morning, at least for me, it's my great pleasure to introduce to you our speaker for this session, Colin Defant. Welcome, Colin. Well, I was ready to say that Colin is a 5th year PhD student at Princeton Uni, but actually just like Sam this morning, Colin did graduate a few weeks ago, maybe a month ago.
Yeah.
And so he's now officially a doctor. So once again, it's something we can all look up to. So congratulations. And so he will be moving from Princeton Uni, where he was studying under the supervision of Noah Kravitz. Everybody know him, I guess. And he will be moving to MIT and Harvard in Cambridge, Massachusetts. So congrats on that too. And to give you a bit of feedback, when we started brainstorming names for the conferences, to be honest, I did not know you, Colin. But several of my colleagues, at least 3 of them, had put your name just there on the top of the list of candidates. So I remember that I went to check you up and I say, okay, who's the lad? I'm gonna have a look. And I went to see your website. And the first thought I remember was, damn, the guy has a CV with more pages than I have publications. So it's like, okay, I'm gonna feel bad after reading that CV, but okay, and I went through it. And so Colin's work is in algebraic and enumerative combinatorics, but he's gonna present that topic with you, and he has done some impressive work on the field. But what's really impressive is that he somehow still finds the time to be usually active in undergrad research, and he does a lot of mentoring for some years now. And so he works and publishes with many undergrad students, which is I find amazing. And he also mentor high school students. So for that, I congratulate you, because it's something we should all try to do as much as possible. And we know that that has a huge impact on students for later years. So congratulations on that. And so you should all check out his website. He has a list of all the mentoring he does and what you might find interesting, and you might try to do the same later. So that's something you should all do. So we could all say that he has some ferocious appetite, and some of you might know exactly what I mean by here if you've seen his website. And so yeah, after his talk, not now, of course, I invite you to check his website. Look, as he has other presentations there of the talks he made on YouTube. You have different ones too, on stack sorting, on different topics. So it's I'm pretty amazed, and I'm really happy to have Colin with us today. So yeah, Colin, the floor is yours.
All right. Well, yeah, thanks for the wonderful introduction. That was pretty much like the best introduction I've seen for me. So that was very nice. Let me connect or share my screen. Give me just a second. Okay. But yeah, also, I guess I want to thank the organizers for putting this all together and making this conference happen, because I think it's just such a cool idea to have this being like by graduate students and for graduate students. And yeah, I think it's a great idea. So I'm glad that it was able to happen. But yeah, I guess I will tell you about variants of promotion. And this is living of what's called dynamical algebraic combinatorics. And basically the goal of this area, roughly speaking, is to take some set X of interesting combinatorial objects and look at some specific function f from X to itself, which is defined in some interesting way. And we want to study the dynamics of f. In other words, we want to iterate it and just look at what happens to these interesting objects as we repeatedly apply f to them. And the specific function that I'm going to be telling you about today is called promotion. And it acts on the set of linear extensions of a fixed finite poset. So let me start with posets. So the word poset here is short for partially ordered set. So it's a set P together with some partial order relation less than or equal to sub P. There is a formal definition of what a partial order is. It's a relation that is reflexive and antisymmetric and transitive. But intuitively, I think it's easier to think about a poset in terms of its Hasse diagram, which you can imagine is just some graph that's kind of embedded in the plane so that the edges are upward. So we imagine that these edges here are sort of directed in the upward direction. And then the convention is that if we have two y in our poset, which will be represented by vertices, then we say x is less than y if there's an upward directed path going from x up to y. It says my internet connection is unstable, but hopefully it's okay. I mean, I can speak slowly if that helps, but okay.
It's okay on my end.
Okay.
It's okay.
Cool. So anyway, if this was x and y, for example, then we would say x is less than y in the poset because there's this upward directed path going from x up to y. On the other hand, if x and y were like this, then we would say x and y are incomparable because neither one is bigger than the other. Okay. So a labeling of a poset P is just a bijection from P to the set of integers from 1 to n. So I'll imagine n is the number of elements of P. And I'm going to let lambda sub P be the set of labelings of P. So as an example, here's a labeling of my poset. I've just assigned each element some label, which is a number from 1 to 5. Now, a special type of labeling is what's called a linear extension. You can think of this as a labeling that preserves the order structure in the sense that whenever x is less than or equal to y in the poset, that forces the label of x to be less than or equal to the label of y as numbers. So you can think of it as being kind of sorted into the correct order so that the numbers increase as you go up the Hasse diagram. And here's an example of a linear extension. You can see if I just start walking up, the number should be increasing as I go up. And I'm going to let this script L of P be the set of linear extensions of P. So promotion is this special bijective operator that sends linear extensions of P to linear extensions of P. And there are a couple of different ways of defining this. So I'll start with a definition using what's called jeu de taquin. So this is, I guess, French for a game of teasing. And this is originally defined by Schutzenberger. So this goes through a 3-step process. The first step says, take the label 1 and look for the smallest label that's above it in the poset and just swap the 1 with that label. And then just keep doing this. At each step, swap the 1 with the smallest label that's above it until finally there's nothing left above the 1. And then step 2 says just change the number 1 to n plus 1. And then finally, step 3 is decrease every label by 1. So let me do an example of this. Here's a linear extension of some poset. So the first step says 1 with the smallest label that's above it. Well, the smallest label above the 1 is the 2. So I'm going to swap the 1 with the 2. And now I keep doing this. The next step is, well, I still swap the 1 with the smallest label above it, which is the 5 now. So I'm going to swap the 1 with the 5. And now again, I swap the 1 with the smallest label that's above it, which in this case is the 6. And now there's nothing left above 1, so that completes the first step. The second step says just change 1 to n plus 1. Here n is 6, so I'm going to change the 1 here to a 7. And then finally, the last steps decrease every label by 1. So the 2 becomes a 1. The 3 becomes a 2. The 4 becomes a 3. The 5 becomes a 4. 6 becomes a 5. And the 7. And so now this is some new linear extension of our poset. Okay. So maybe I'll say for one thing why you might care about this. I mean, or why people have cared about this, because it might seem kind of strange and sort of artificial, but this is originally defined by Schütz and Berger in order to understand properties of the Robinson-Shenstedt-Knuth correspondence. And then later people found that it has other applications and appearances in algebraic combinatorics. So for example, Edelman and Green found a nice way of using promotion to understand the reduced words for the longest element of the symmetric group. And there are various other applications coming from algebraic combinatorics. So there is motivation for this. But from a dynamical point of view, we can just say, well, this is some bijective operator, and we want to understand the dynamics. So here, dynamics of promotion looks like on the set of linear extensions of this. So there are 5 linear extensions here, and you can see they break up into one orbit of size 2 and an orbit of size 3. So one of the things we might want to understand is what are the orbit sizes? Can we describe the sizes of these orbits that are showing up? But before I say something about it, let me give a definition of promotion, which uses what are called toggles. These are also sometimes called Bender-Knuth involutions. So what I'm going to do is say, if I have a linear extension sigma, and I take some integer I from 1 to n minus 1, then I'm going to let sub I of sigma be a new linear extension that I get from sigma by doing a small local change. And what this small local change does is, well, I wrote it out here in symbols, but basically look at the labels I and I plus 1. And if I is sitting below I plus 1 in the poset, then just don't do anything. Just do nothing at all. And if I is not below I plus 1, then just swap those labels. Swap I plus 1 labels. And then promotion, composition of toggles where you do tau 1 and then tau 2 and then tau 3, tau n minus 1. So let me do this in this example. This is the same linear extension that I had from before. And you'll see we end up getting the same result. So first I do tau 1. So tau 1 says, look at the labels 1 and 2. And since the 1 is below the 2, I do nothing. Just leave them alone. Now I do tau 2. Tau 2 says, look at the labels 2 and 3. And since the 2 is not below the 3, I'm going to swap them. So the 2 and the 3 swap. And now I do tau 3, which says, look at the labels 3 and 4. 3 is not below 4, swap them. Now I'll look at the labels 4 and 5. 4 is below 5, so I do nothing. And then finally, I do tau 5, which says, look at the labels 5 and 6. 5 is, I do nothing. And so this completes promotion. So now linear extension, and you can check that this is exactly the same as what I got up here when I did this using Jura-Takan. So it is actually the same map. Maybe it's not just look at this for the first time. I think certainly for me, it was not obvious. But it's sort of a nice exercise to just try to convince yourself that these are the same. And I think the best way to do this is to sort of write out a sufficiently large example and kind of just stare at it for a while until you say like, oh yeah, okay, I see why these are sort of doing the same thing. Or if you want, there's also a survey article by Richard Stanley called Promotion and Evacuation. And he goes through writing out like a rigorous proof of this in the survey. But I mean, it's not terribly difficult. You just kind of have to write out an example and like stare at it for a few minutes. Okay, so here are theorems about the dynamics of promotion. So Schütz and Berger back in 1977 showed that if you have a rectangular poset, that I mean, it's just a poset whose Hasse diagram looks like this. So it's like a rectangle. This would be the 3 by 5 rectangular poset. In this case, the order of promotion acting on the linear extensions is equal to the number of elements of the poset. So by order, I just mean it's the least common multiple of the orbit sizes, or in other words, it's the smallest positive integer such that if you apply promotion that many times to any linear extension, then you get back to where you started. And you can see that this theorem is true out before, because this is a rectangular poset up here. I guess it's scrolling up. Okay, so this is a rectangular poset. It has 6 elements, and the order of promotion here is 6 because it's the least common multiple of 2, 3. Okay. So then later, Edelman and Green, and they were studying the reduced words for the longest element of the symmetric group. They showed that if P is a poset that looks like this, this is a type A root poset. And okay, so I won't say exactly what this is in words, but, or you can sort of imagine that like, okay, this would be the next smallest, and then this would be the next smallest one. So there's sort of this increasing sequence of these posets that look like this. And their theorem says that promotion acting on the set of linear extensions here has order 2 times the number of elements of the poset. And then later, Heyman showed that there are some other nice families of posets where promotion has well-behaved orbit structure. So he said you could look at a shifted double staircase. This is basically a poset that looks like this, where you take a kind of triangle thing and you glue on another little triangle or something. I won't define what it is formally, but you can imagine it's some kind of nice family of posets. He shows that in this case, the order is equal to the number of elements. And then this is true if you look at what's called a shifted trapezoid, which is basically something like this, where you can see it's like sort of a trapezoid here. So these are, well, actually for a while, these were the only examples of nice families of posets where it was known that promotion had interesting, well-behaved orbit structure. Very recently, Hopkins and Ruby found another class of examples. So they looked at what's called the chain of V's. So here they're just taking this 3-element V-shaped poset like this, and they're just making a chain of them. This would be the 4th chain of V's poset. And they showed that in this case, the order of is the number of elements of the poset. So again, these are basically the only examples where it's known that promotion has well-behaved orbit structure. Basically, if you choose pretty much any other just random poset, chances are the orbit structure is going to be very wild and unpredictable, and there's very little that we can say about it. So really, when you have these very nice specific examples, they're really like these rare gems that are really nice to have. And I'll also just mention that here I was talking about the order of promotion. So that's like the least common multiple of the orbit sizes. But there are also some results that allow you to say something more precise about the entire set of orbit sizes. So for example, there's this theorem due to Brendan Rhodes from 2010, where he uses Kazhdan-Lusztig theory to prove that when you look at promotion acting on the linear extensions of a rectangular poset, so here this is for a rectangular poset, he shows that this satisfies what's called the cyclic sieving phenomenon. So I'm not going to say exactly what the cyclic sieving phenomenon is, but basically it's this phenomenon that allows you to say exactly what the orbit structure of this operator is. So you can describe what all of the orbit sizes are and how many orbits there are of various sizes. And you can kind of encode this in a very elegant way by using some specific polynomial. So it's a really nice result. And it says that, you know, we can actually say something very precise about the orbit structure in certain cases. Okay, so that's all I'm going to say about sort of classical promotion. But now I want to tell you about a couple of variants of promotion that I've studied. And the first one I'll call promotion sorting. The idea here is to try to take promotion and extend it from linear extensions to the set of all labelings of your poset. And here we're going to get a non-invertible map. Okay, so it's not going to be a bijection anymore, but it'll be some non-invertible map, and we can still try to understand dynamics. And I should mention that this idea to extend promotion to the set of labelings is originally due to Jim Prompt. So he suggested this kind of idea, and then I gave a certain definition, and I studied this later with Noah Kravitz. So this whole stuff about promotion sorting is joint work with Noah Kravitz, and it's building off of this idea of Jim Prompt. Okay, so as before, there are two definitions. One is using jeu de Tacan, one is using toggles. They end up being equivalent. And the definitions are actually exactly the same as what I had before. And that's because I intentionally a few slides ago for promotion extend immediately to this more general promotion sort. So again, the definition using jeu de Tacan is to say you swap one with the smallest label above it, and you keep doing this until there's nothing above one. And then you change the one to an n+1, and then you decrease every label by one. So let me do this example here. Notice this is not a linear extension, it's just some labeling. And so the first step says, okay, swap one with the smallest label that's above it. The smallest label that is above the, you can check, is the 3. So I'm going to swap the 1 with the 3. And now I do this again. Now the smallest label that's above the 1, 4. So I'm going to swap the 1 with the 4. And now there's nothing left above 1. So that completes the first step. The second step says change the 1 to an n+1. So here n is 12. So I'm going to change the 1 to a 13. And then finally, I decrease every label by 1. So to make this a little faster, let me just write down all of the new labels next to the old ones, and then I'll erase the old one. The 5 will become a 4, 2 becomes a 1, 10 becomes 9, 12 becomes 11, 3 becomes 2, 6 becomes 5, 9 becomes 8, 11 becomes 10, 8 becomes 7, 4 becomes 3, 7 becomes 6, and 13 becomes 12, and then I'll just erase the old ones. Okay, so this is our new labeling, and this is promotion of the old labeling. And as before, there's an alternative definition which uses toggles. And it's, again, it's the same thing that I defined earlier, except now for labelings. As we say, if you have any labeling sigma, and you have an integer I from 1 to n-1, then we're going to let tau I of sigma be this new that we get by doing a small local move. And again, the small local move just says, look at the numbers I and I+1. And if I is below I+1, you do nothing. And if I is not below I+1, you swap them. And then promotion, again, is this composition of toggles. So let me do this example here. So first I do tau 1, which says swap the, or look at the labels 1 and 2. And since 1 is not below 2, I'm going to swap them. And now I do tau 2, which says look at the labels 2 and 3. Here 2 is below 3, so I do nothing. Now I do tau 3, which says look at the labels 3 and 4. Since 3 is below 4, I'm going to do nothing. Next, I'm going to do tau 4, which says look at the labels 4 and 5. Since 4 is not below 5, I swap them. Okay, now I do tau, look at 5 and 6. 5 is not below 6, so I swap them. And okay, at this point, it's going to be a little repetitive, so let me just do this pretty quickly. Next, I look at 6 and 7, not below 7, so I swap them. Now I look at 7 and 8. 7 is not below 8, so I swap them. Now I look at 8 and 9. 8 is not below 9, so I swap them. Oops. Sorry about that. Okay. Okay, so now, hopefully, okay. Now I look at 9 and 10. 9 is not below 10, so I swap them. Now I look at 10 and 11. 10 is not below 11, so I swap them. And finally, I look at 11 and 12. 11 is not below 12, so I swap them. And now I have finally this new labeling, which is promotion of the original labeling. You can check that this is the same as the labeling that I got up here when I did this using jeu de Tacan. And that's because, again, these two definitions are equivalent and the proof is the same. You basically just write down a sufficiently large example and stare at it for long enough. Or a survey article by Richard Stanley, it's essentially the same argument there. Okay, so this is some operator that's acting on these labelings. Again, it's not invertible, but we can still look at the dynamics. So here's a picture showing the dynamics of this extended promotion acting on the labelings of this V-shaped poset. You can see there are two linear extensions down here, which form a 2 cycle. And then all of the other labelings kind of funnel into this 2 cycle. And then here's what happens with this upside down V poset. So again, there are 2 linear extensions that form a 2 cycle, and all these other labelings kind of funnel into the 2 cycle. Okay, so before I say actual theorems about this promotion sorting, let me just give a couple of extra definitions involving posets. So an order ideal of a poset is just a subset that's closed downward, in the sense that if x is less than or equal to y in the poset and y is an element of the order ideal, then that forces x to also be in the order ideal. And as an example, if this is my poset and I look at this set of red circled elements here, that forms an order ideal. And an anti-chain is a subset that has the property that any 2 elements are incomparable. So as an example, these 2 red circled elements here form an anti-chain because, well, there are just 2 of them and they're incomparable to each other in this poset.
Colin?
Yes.
Yeah, there was a question, sorry, 30 seconds ago.
Sure.
I missed it. From Mark, I think on the algorithm above, he asked, and Mark, I can put you on mute if you want. He asked if you perform this algorithm on a chain instead of, I guess, a full poset, do you end up with some sorting algorithm?
Yeah, that's actually a really good question. There is something called bubble sort, where you are basically just, if you think of it in terms of the toggles, you're sort of going up your chain, and you can think of your labeling of a chain as just a permutation. And you're basically just saying, look at the ith number, or, okay, so maybe this is the inverse of it, but basically bubble sort compares I and I plus 1 and swaps them, if doing so puts them into the correct order. And that's composition of toggles is doing. So yeah, in the case of a chain, you just recover this thing called bubble sort that people have studied before.
Okay, thanks.
Right. Yep. Okay, so yeah, an anti-chain is just a subset such that any 2 elements are incomparable. Okay, so here is a theorem about this promotion sorting. So first I'm going to say, okay, let P be some poset with in elements. The theorem, which is joint with Noah Kravitz, says that if you apply promotion, or this extended promotion, n-1 times to the set of labelings of your poset, then you'll get exactly the set of linear extensions. So first of all, if you just restrict this extended promotion to the set of linear extensions, you get the original map that I defined at the beginning, and that's because it's exactly the same definition. I literally just copy and pasted it when I made the slides. But so this is going to restrict to some bijective operator on the linear extensions. But the point of this is that if you apply promotion to some other labeling and you just keep doing this, eventually you'll get to the linear extensions. And in fact, this says that if you apply promotion n-1 times, you'll always get to a linear extension. And this motivates us to define what we call the sorting time of a labeling. It's just the smallest non-negative integer t, such that applying promotion t times to that labeling gives you a linear extension. Right, so just think of this as like the smallest number of times that I need to do promotion to get to a linear extension from my starting point. And what this theorem is saying is that every labeling has sorting time at most n-1. But you might, maybe I have a poset with an element, but how do I know that it actually has a labeling with sorting time n-1? Maybe all of the labelings have smaller sorting time. And this theorem sort of addresses that there exists a labeling with sorting time n-k-1 if and only if the poset has an order ideal of size 2 that is not an anti-chain. For example, if k is 0, this is just saying that there exists a labeling with sorting time n-1, which is like the maximum possible labeling of an n-element poset could have. This only if the poset has an order ideal of size 2 that is not an anti-chain. Here's an example of this with the sort of upside down V poset. this does not have a labeling with sorting time n-1. In this case, n-1 is 2. And that's because it does not have an order ideal of size 2 that is not an anti-chain. Now, this poset does have an order ideal of size 2. Like you could just take the bottom 2 elements here. That's an order ideal of size 2, but that's an anti-chain, so it doesn't count. So we're only looking at like non-anti-chain order ideals. And this example you can see is actually true if I go back up to my dynamics that I wrote up here. So you can see that it's taking a while to scroll up. Okay. Well, there are these 2 linear extensions down here at the bottom, and they have sorting time 0. And then there are these other labelings, each of which has sorting time 1, but none of the labelings have sorting time 2. So this agrees with that example that I was saying. On the other hand, if I go up to this V-shaped poset, there are labelings with sorting time n-1, which is 2, right? Namely these up here. And you can see that's because this poset does have an order ideal of size 2 that is not an anti-chain, right? For example, you could just look at these 2 elements. They form an order ideal, and it's not an anti-chain. Okay. So this motivated us to define what we call tangled labelings. We'll say a labeling of a poset is tangled if it has sorting time equal to n-1, which again is like the maximum possible sorting time that a labeling of an n-element poset could have. And one of the things we tried to do with this is count how many tangled labelings a poset could actually have, right? So I have some poset and I want to know how many tangled labelings does it actually have. And we did this not for all posets, but for a large class of posets that we call inflated rooted forests. I'm not going to say exactly what an inflated rooted forest is, but I'll give you a couple of special cases that I think are sort of nice special cases. So the first special case is just when your poset has a unique minimal element. And in this case, it turns out there are exactly n-1 factorial tangled labelings. And actually, we can describe what they are very explicitly. These are exactly the labelings in which the unique minimal element is given the label n. Right? So it should make sense that maybe this is kind of like far from being sorted in the sense that you've put the biggest possible label on the bottom element. So it's kind of makes sense that this is far from being sorted. Maybe I should also say, in case this wasn't clear, that the name tangled is coming from the fact that this is very far from being sorted. So it's like tangled up and messy in some kind of way. So that's one special case. Another special case that I think is actually more interesting is when the poset is a rooted tree. So a rooted tree is just a poset whose Hasse diagram looks something like a tree that has a root vertex up at the top, and then everything grows down from the root. Here I'm going to call the root R. So this would be R up here. I guess a formal way of saying what a rooted tree is it's a poset that has a unique maximal element. That's the root. And it also has the property that every other element in the poset is covered by a unique thing, which is its parent. Right? So there's exactly one thing right above it in the poset. Just a little bit of notation here. If I take any element v in my poset, I'm going to let p sub less than or equal to v be the set of elements that are less than or equal to v in the poset. And similarly, I'll let p sub greater than or equal to v be the set of elements that are greater than or equal to v in the poset. And then for any element v that is not the root, remember this means that there's a unique element right above it, which is called its parent, and I'll denote that by v star. So as an example, if I took, say this was v here, then this element right above it is v star. And then the theorem says that the number of tangled labelings of my rooted tree poset P is n-1 factorial times this sum of products. So the sum here I'll zoom in and kind of go through this a little slowly. The sum is ranging over all of the leaves of the tree, which are just the minimal elements of the poset. And for every leaf L, we're going to take a product over all of the elements V that are greater than or equal to L and not the root. Okay. So the product is just over all the things that are greater than or equal to this leaf, but not the root. And then the term in the product corresponding to this v is just the number of things that are less than or equal to v minus 1 divided by the number of things that are less than or equal to the parent of v minus 2. Okay, so this is some explicit formula. I think it's kind of nice. I mean, I don't know. It's simple enough that I can write it down in one line and it has this sort of nice form, but it's also maybe complicated enough to actually be interesting and have a non-trivial proof. But anyway, this is what we can say about tangled labelings in these special cases. And I'll just mention we have this conjecture, which I personally like. I think this is, or it would be very nice if someone could resolve this. It says that if you take any poset with n elements, then it should have at most n minus 1 factorial tangled labelings. And this is true for the inflated rooted forest. So I haven't told you what inflated rooted forests are, but this is true for those. And you can see it's true certainly when the poset has a unique minimal element, right? Because then, well, it has exactly n minus 1 factorial tangled labelings. But it's also true, you can check for the rooted tree, because you can show that this sum of products is less than or equal to 1. Okay. So are there any questions up to here about the promotion sorting? Because now I'm going to move on to the next variant. Okay, if not, then I will go to toric promotion. And here I'm going to be working in a sort of graph theoretic setting. So it's going to be very similar to the poset setting, but I want to use graphs for a specific reason. So here I'm going to let G be a simple graph with vertex set V and edge set E. A labeling of my graph is just going to be a bijection from the vertex set to the set of integers from 1 to n. And I'm going to let lambda sub G be the set of labelings of G. So as an example, here's a labeling of some graph. I've just put a label next to each vertex. And I want to define toggles kind of in a way that's similar to what I did with the posets, but it might look a little different, but there is a way in which this is very similar. So for any number I from 1 to n and any labeling sigma, I'm going to let tau sub I of sigma be this new labeling of my graph that I get by doing this small local change. So what I do is I say, look at the labels I and I plus 1, and if they are sitting on adjacent vertices, I do nothing. But if they're sitting on non-adjacent vertices, I swap them. Okay, so this is what this is saying in symbols. But again, it's just you look at I and I plus 1, and if they're adjacent, you do nothing. If they're not adjacent, you swap them. And I'll point out that this is taking the numbers mod n. So I'm also defining this when I is equal to n. And in that case, you just do this with the numbers n and 1. Again, if they're adjacent, you do nothing. And if they're non-adjacent, you swap them. And then I'll define promotion to be this composition of toggles, tau 1, tau 2, all the way up to tau n minus 1. So it looks just like before. And there is a specific way in which this is basically equivalent to what I've defined before. I won't go into that, but you can imagine that this at least looks similar to what I was doing in the poset setting. But the new definition here is that of toric promotion. And it's very similar, but it's different in a key way. Here we just do tau 1 and then tau 2 and so on up to tau n minus 1. And then we do tau n at the end. So in other words, we're doing the full promotion, but then we're tacking on this extra tau n operator, which looks at the numbers n and 1. So you can think of this as like a cyclic analog of motion because you're kind of wrapping around and also looking at the numbers n and 1. So let me do an example of this. Here I just have a labeling of a path graph. So I'm going to copy this labeling and manipulate it down here. Okay, so I want to do toric promotion. The first tau 1, which says look at the labels 1 and 2, and since they are not adjacent, I'm going to swap them. Okay, so swap the 1 and the 2. Next, I'm going to do tau 2, which says look at the labels 2 and 3. And since they are adjacent, I do nothing. Now I do tau 3, which says look at the labels 3 and 4. They are adjacent, so I do nothing. Now which says look at the labels 4 and 5. they're not adjacent, so I swap them. And finally, I do tau 5, which says look at the labels 5 and 1, and they are not adjacent, so I swap them. And this is what toric promotion does. It takes this labeling and transforms it into this labeling down here. I also wrote out what this does for the entire orbit, and I kind of hid it over here on the sides. So let me just drag that over. So it turns out that if you keep doing toric promotion, I didn't want to, all the toggles and stuff, but if you keep doing it, you'll end up in this 4 cycle. So this labeling goes to this one, goes to this one, goes to this one, and then you end up back where you started. And I think if you stare at this for a second, so obvious what this operator is doing, even a path graph, right? Like even you might think, okay, a path graph, it's very simple. What could it be? But I think when you look at this, it's like, what is this actually doing to go from this labeling to this? Of course, you can describe it with the toggles, but it's not really clear just from looking at it what it's actually doing kind of from a bird's eye view. So I think it's maybe a little surprising that we can exactly the orbit structure of toric promotion acting on the labelings of a path graph. But not only can we do this for a path graph, but actually any forest graph. So the theorem, this main theorem that I've proven here, says that if G is any forest with at least 2 vertices, and sigma is a labeling, and I want to understand what is the size of the orbit of toric promotion containing this labeling sigma. In other words, how many times do I have to do toric promotion until I get back to sigma? When I look at the label 1 and I look at the vertex where it's sitting, and it's sitting on some connected component in my graph, so I'm going to let T be the number of vertices in that connected component. And then the theorem says that the size of the order of the orbit of toric promotion containing sigma is just n-1 times T over the GCD of T and N. So it's actually a very simple formula, and you can do this for all of the orbits. So this tells you all of the orbit sizes. And one corollary of this is that if G is actually a tree, so like a connected forest, well, in this case, all of the orbits have size n-1. So this is not just saying something about like the order, just like the least common multiple. It's saying like every single orbit has size n-1. And you can see this is true. Well, okay, first of all, why is this true from the formula? It's because, okay, if you have just one connected component, then T is just n. And so here this fraction is just n divided by the GCD of n and n, which is 1. And so you're just left with. And you can see this is true up here in this path graph because this is it is a tree. It has 5 vertices. And this theorem is saying orbit should have size 4. And this orbit has size 4, but I moved it. But it turns out that I could have written down any random labeling here and I still would have gotten an orbit of size 4. And I'll just mention that this is very different from what happens in the case of promotion. So I just defined promotion also in the graph theory setting. You could say, what happens if we just do promotion on the labelings of a path graph? But it turns out it's very wild and unpredictable and hard to understand. For example, even if you just look at a path graph on 7 vertices, the order of promotion there, so like the least common multiple of the orbit sizes, is this massive number here. So it's very different from toric promotion, where all of the orbits are just size n-1. And so I don't really have time to go through the idea. I personally like the proof. I think it's kind of nice and interesting, but I'll just mention some of the ideas that go into the proof, or that allow me to set up the proof, I guess. So one of the useful ideas is to recognize and rewrite toric promotion to the n-1 as C composed with promotion to the n, where here this operator that cyclically permutes the labels 1 through n. So for example, if I apply C to this labeling of this graph here, then I get this labeling where I just said, okay, the 1 becomes the 2, 2 becomes 3, 3 becomes 4, 4 becomes 5, and 5 becomes 1. And you can prove this identity here about to the n-1 being C composed pro to the n just by manipulating toggles in an algebraic way. So once you know that this is like the thing you want to prove, it's not too difficult to actually do it. But the nice thing about this is that C-compose pro can be described very explicitly using some kind of jeu de Tacan sliding thing, where basically what you swap the label 1 with the smallest label that's adjacent to it. And then at each step, you swap the label 1 with the smallest label that's adjacent to it that's bigger than everything it already swapped with. So let me do this. Here I have some graph with some labeling, and I want to start by swapping the 1 with the smallest label that's adjacent to it, which is the 3. So 1 swaps with 3. And now I do this again. Now I'm going to swap the 1 with the smallest label that's adjacent, bigger than everything it already swapped with. Well, it already swapped with the 3, so I swap it now with the 7. And now I try to swap the 1 with the smallest label that's adjacent to it that's bigger than everything it already swapped with. But the 1 already swapped with the 3 and the 7, and nothing adjacent to the 1 bigger than the 7. So now I just get stuck and I stop. So this new labeling is C-compose pro of the original labeling. And I want to represent what I did here with this sort of this red path by saying I basically slid the 1 along this red path. That's all I did. I just kind of slid the 1 along, and the 7 and the 3 just had to move backward 1 step along the path. What's nice about this is that if you have a tree graph, so here we're sort of using the, if you have a tree and you just do C-compose pro multiple times, then the net result will still be described as just sliding 1. So let me give an example of this. Let's say I do C-compose pro again. Well, okay, so now I'm starting over. 1 has not swapped with anything. I'm going to say, okay, 1 swaps with the smallest label that's adjacent to it, which in this case is the 4. So the 1 swaps with the 4. And now I say, okay, 1 swaps with the smallest label adjacent to it that's bigger than everything it already swapped with, but there's nothing adjacent to it that's already swapped with because it swapped with the 4. So at this point, it gets stuck. And this is the next application of C-compose pro. Let me do one more application. So again, okay, I'm going to swap the 1 with the smallest label that's adjacent to it, which is the 4. So 1 swaps with 4. Now I swap the 1 with the smallest label that's adjacent to it that's bigger than everything it already swapped with, which in this case is the 6. And at this point, it gets stuck. So I'll represent this third application of C-compose pro with this orange path here. So the point is, the first time I did C-compose pro, the 1 red path. The second time it went along the blue path. The third time, orange path. But the net effect of all of that was just to slide the 1 along this pink path here. Right? Because basically up here, when I did the blue path and then this next step, orange path, they kind of canceled. I just slid the 1 up and then I slid it. And in general, you'll get this cancellation so that the neck is always just sliding the 1 along some path. So the point is, this gives you a nice way of understanding what C-compose pro is doing. And then since this is related to toric promotion with this identity up here, which I'm circling, this allows you to understand things about toric promotion. But there is more work that goes into this. You have to explain more things about where is the number 1 actually sliding. Actually, I can say something about that. It turns out when you keep doing C-compose pro, the 1 will visit every x until it eventually gets back to where it started. So it actually goes through the entire graph before going back to where it started. For example, here, the 1 originally started out on this vertex, and then it slid along the red path to here, and then it slid to here, and then down to here. If I did it again, I think it would slide up to this vertex, and it ends up just visiting every vertex until going back to this one where it started. Okay, so that's basically all I'm going to say about toric promotion. And I believe that is everything that I have. So thank you.
Thank you, Colin. So please join me in give some applause. We've got some nice emoji here. So I'm lucky I can clap for you in person. It was very nice and very nice talk. So if people have some questions, you can use the Q&A features of Zoom. and we will have a look. If you use the chat, I will have a look too. It's fine. So there is a question by Kyle, and he asks, people, I'm gonna read it because people cannot see it, is can you describe how toric promotion affects the number of descent of labeling on the path, though of as a permutation in one line notation? Relatedly, is there some permutation statistic that is fixed by toric promotion?
Right. So I don't know about the second part, about the statistic that is fixed, but yeah, I can say something about the descents. Let me make sure I get this right. I think what is going to happen is, so let me imagine drawing arrows on my path to represent when I have a descent or an ascent. So I'll basically direct my edge from the smaller label to the bigger one. So here I would go from 2 to 5, I would go from 1 to 5, from 1 to 3, and from 3 to 4. And these arrows are basically encoding the descents by saying that when you have a right arrow, that's an ascent, and when you have a left arrow, you have a descent. And I think there should be a simple way of explaining what happens to the descents or these arrows when you do toric promotion. Let me see what happens here. So what ended up happening was, I think the one, what is actually happening? It should be, well, I want to say that like there should be some kind of equidistribution result about the descents because the one is visiting every, oh no, I see. It's a little, okay. The reason it's a little weird is because there is something nice if you do C compose pro. So I was getting compose pro. I think if you do this operator, you can understand the descents pretty easily, but it's a little weirder for the actual toric promotion. But yeah, I guess, yeah. So for toric promotion, I think there's not a super nice description, but for C compose pro, I think it's not hard to find patterns in what the descents are doing.
Okay, thanks. There is another question, is when you explain that the power of T pro can be expressed as the power of C pro, is that true for any graph or just for trees?
Yeah. So this is true for any graph. Yeah, I should have said that. This you can prove it's for any graph, but then this part is where I have to use the fact that it's a tree to get this composition of the C compose pro having a nice form.
A lot of question now. Mark Denker is following us on his first question on bubble sort, and it says that it seems like promotion sort is kind of an extension of bubble sort to arbitrary posets. Mm-hmm. And have you considered extending other sorting algorithm to posets?
Let's see. I mean, in some vague sense, well, no, I have not really considered this. I guess, I mean, okay, so I've looked a lot at something called stack sorting. I have not thought about doing this for other posts. Maybe there's a way to do that. I actually haven't really thought about that as far as I remember. But yeah, I guess the short answer is I haven't really thought about doing this.
And Afsane is asking, so on the conjecture you had on number of tangle labeling, what extra tool would you need or ideas to kind of prove your conjectures, you think? The conjectures on that you have at most n-1 factor.
Oh, I see. Tangle. Yeah. Yeah, I'm not so sure. I thought about this a little, but didn't really have any ideas. I think, I mean, it's possible that maybe there could be some kind of, but yeah, I'm not sure. I guess I tried a few things and nothing really seemed to work. So yeah, I don't know.
Okay. And if I have one minute, I might have one myself, is in the Tugger notation for any one of these kind of promotion actually. What happens is instead of, because you make them in a specific order, what happens if you kind of permute them? Like if you study the together with the specific permutations?
Yeah, okay, I think that, yeah, that's great. So for toric promotion, I have started looking at this with someone who was a student of mine in an undergrad research program last summer, and we're sort of investigating what happens even just on a path graph. It's not so obvious what's going on, but we're looking at exactly that question in the case of a path graph, but doing the toggles in some kind of other order. And we're observing that there are interesting things happening, but we are in the process of trying to figure out like what actually it is. Then I guess another, I mean, so you could do this for you know, the promotion sorting, but even for promotion, like just linear extensions, I don't know if this has been studied that much. I think maybe people have said like, okay, maybe there's not motivation coming from the algebraic context, so maybe that's why people haven't looked at it. But I think it's a very natural thing to do dynamically. And yeah, I think that would be something that I think people should look at more, trying to understand just in the classical sense of promotion acting on linear extensions. What happens if you do some other toggle order? There might be something about this. I think people often will do something where you look at like, do all of the toggles that have odd indices and then all of the ones with even indices. That's kind of a natural order. So maybe someone's done something with that. But I think for like arbitrary orders, I haven't seen anything about that.
Okay, thank you. Yeah, that was my contribution. Okay, so if there's no more question, please join me again in thanking Colin. It was very nice presentation.